Hello, everyone. This is Lin Chen from Zhejiang University, and I will present an improved pseudopolynomial time algorithm for subset sum. This is a joint work with Lian, Mao, and Zhang from Zhejiang University. So we studied the classic subset sum problem. In this problem, given is a multiset of n positive integers and the target t. Our goal is to decide whether there exists a subset Y whose sum is exactly T. In other words, we want to know whether T can be hit by subset sums. There are several reasons for studying this problem. So first, this is among the most fundamental NP-hard problem. It is a special case of many other important problems in computer science, including knapsack integer programming, and so on. So it naturally finds applications in many other problems. And a better algorithms for subset sum can potentially benefit the algorithmic design for those problems. Moreover, subset sum receives considerable attention from both the theoretical computer science community and additive combinatorics community. In recent years, there has been a series of works that combines techniques from both fields to make progress in algorithms. And my talk is also along this line of research. So now I will briefly talk about relevant works. This table summarizes the progress in pseudopolynomial time algorithm for subset sum. And here, recall that T is a target and W refers to the largest input integer. Taking N and T as the input parameter, so far the best known result is by Brinkman and Jing and Wu. I also want to mention that there also exists a order of N time algorithm if the input is dense. That is, when n is very large and at least a square root of w. In this case, if t is not too far away from the middle, then within order of n time, we can solve subset sum. But in general, order n plus t is the best we can do. When taking n and w as the parameter, so far the best known result is order n plus w to the power of 1.5. We know that w is always smaller than t, so it is a more preferable parameter. But on the other hand, we can also see that in terms of n and w, we are still a bit far away from linear now. There is also a conditional lower bound that states that we cannot get better than linear time in n and w. So the major open problem in this direction is whether we can get order of n plus w. In this paper, we make progress by presenting a order of n plus square root of w times t time algorithm. As the best known prior result is order n plus t, and the major open problem is order n plus w, we kind of get into the middle point of the whole journey. As a side result, we also obtain order n plus w to the power of 1.25. But in this case, we would require the input to be a set. All the other results, they actually works if the input is a multiset. Okay, so now I will briefly talk about the techniques. We use S of x to denote all subset sums of x. For two integer sets a and b, we will use a plus b to denote their subset. And this will be given by adding arbitrary pairs of integers from a and b. Use this notation, we can set up a tree-like framework that recursively computes S of x from bottom up. Such a framework has been utilized in several prior papers. So here, to compute the sum set of two sets, we will use sparse fast Fourier transform, which runs in near linear time in the input and output size. So we see that if we just naively follow this framework, the overall running time would be n times w, or the order of t. To get a better running time, we will leverage additive combinatorics results, and this works like this. So we will try to compute the node, each node that represents a subset of some subset. And if at certain layer, the sum of the cardinality of the nodes is small, then we just use sparse fast Fourier transform. If the sum of their cardinalities is large, then we stop the computation and assert that T can be hit. And the tool for making the decision, making the assertion is in additive combinatorics. We use, this is due to Samredi and Wu, which basically says that if you get a sequence of sets where all integers are within U, if the sum of their cardinalities exceeds U, then their subset must contain an arithmetic progression of at least U terms. Here we want to remark that the additive combinatorics result does not tell us the value of the common difference delta. This is only an existence statement. All we know is just an upper bound of this delta based on the fact that the largest term in this AP is no more than the summation of the largest integers in each set. And so the common difference cannot be too large given that this AP is very long. Okay, so as you can see here. Now we can come back to our tree-like computation framework. In an earlier work by me, I have utilized this sparse versus dense method to obtain a linear time approximation scheme for subset sum. And the key observation is that in approximation world, if the largest integer within a set is too big, we can round it down to an order of 1 over epsilon. And we do this rounding because remember that the overall running time is actually depends on the summation of cardinalities. And on the other hand, the additive combinatorics result requires the summation of cardinalities to be controlled by the largest integer. And so bounding the largest integer is essentially bounding the overall running time. So when we move from the approximation algorithm to exact algorithm, the major challenge is that we cannot round anymore. And so the largest integer within the set will actually keep growing when we perform the bottom-up computation. At the root, the largest integer becomes the summation of all the integers, and this becomes n times w. So this framework will not offer any benefit than a straightforward computation. So to overcome this challenge, our basic idea is like this. So first, we can randomly permute the input integers. And this guarantees that if a layer contains L nodes, let's say, then each xi out of this L node will contribute roughly 1 over L fraction of the T. Indeed, so if you just perform a little bit probabilistic argument, then you will see that with high probability, the contribution of each xi will lie within some small interval. And the length of the interval is roughly root of w times t. And this square root basically comes from a central limit type of inequality. And so if the whole length of the interval is small, then if we translate the whole interval, we can make sure that the largest integer within each interval, within each subset is reduced to the length of the interval, and therefore bounded by square root of w times t. So after controlling the largest integer, we are not done yet, because we only show that t will lie within some long arithmetic progression. And this only guarantees that there exists some subset sum which is not far away from t. So this only guarantees that t is approximately hit but not exactly hit. So to go from approximately hit to exactly hit, we shall extend an idea from dense subset sum. So I will very roughly describe the high-level idea from dense subset sum. Okay, we will further generalize it. And this core idea actually dates back to even earlier work in additive combinatorics in 1980s. So let's say we can partition the input into two disjoint subsets, the AP set A and the residue set R. So the AP set will contain a very long arithmetic progression of some common difference delta. And the residue set R will contain all residues of delta. Then we can claim that T lies in their subset. Why? So I think with this figure, this becomes fairly clear. So here we use the length of a line segment to represent the value of an integer. So a longer line means a larger integer. So whenever S of R here contains all residues of delta, and S of A here contain all multiples of delta, then we know that because T can always be expressed as some residue plus some multiple of delta, so it must be hit. But this will require this AP to be extremely long because we need all multiples of delta. So slightly generalizing this idea, it is sufficient that if the AP set contains a moderately long AP and T lies deep within the AP. So what does that mean? So again, so let's see this figure. So suppose we know that T lies within this AP, okay? And if we can further guarantee that if we just subtract any residue from T, okay, any residue here from T, if we can still guarantee that this result will lie within this AP, then we know T can be approximately hit because T must be expressed as some residue plus some multiple, and we guarantee that this lies within this AP. So in this way, we only need to make sure that this AP covers a wide range whose length is at least R max, the largest residue. Okay. So following this idea, what we can do is to partition the input into the AP set and a residue set. And this AP set will further consist of a good subset G that generates a moderately long AP and a reposition set D that relocate the AP so that T lies deep inside it. And the residue set should contain all residues modulo delta. So it should contain delta input integers that are co-prime to delta. And some of you might feel that R contains too many integers, but if you think in the worst case, it's possible that every input integer modulo delta is 1. And in this case, you need delta integers in order to make the residue of delta minus 1, right? So following this argument, the common difference delta and the number of terms m of the AP have to satisfy certain conditions. And so the question is whether these conditions are true from additive combinatorics. And the short answer is yes, if we set the dense versus sparse threshold by root of W times T. And this will follow from some calculation, but I will skip that because that's not difficult. And you can refer to our paper for details. So now let me just summarize everything and present the algorithm as a whole. So what we do is that we will first select the root of T over W integers out of the input to form the residue set R. And here these integers need to be selected strategically in the sense that it's universal. That is, it can serve as a residue set for all possible delta. And the reason is that, again, so as we said, the existing result in additive combinatorics does not tell us the value of the common difference, but only provide an upper bound. So we have to make sure that this works for all possible delta. And if so, we cannot find out such a residue set, then it means almost every integer is a multiple of some common divisor. And we can somehow divide this common divisor and work on the reduced instance. Okay, this is a very rough sketch. And so now, after we do this, we can compute S of R. because R only contains a few integers, this can be done efficiently. So finally, we perform the tree-like computation for S of x minus R. And if it is sparse, we will get this set, and we can further compute its subset with S of R. And again, so because the largest integer in S of R is small, the subset can be computed via standard FFT. And if we are in the dense case, then just return yes directly. So at the end, I would like to remark that if you read our paper, you may find some of the inequality appear a little bit loose, especially when it involves the common difference delta. And the reason is due to that we do not know the value, so we have to stick to the worst case. And this perhaps suggests that while additive combinatorics results proves to be particularly useful in recent progress in algorithms, there still seems to be some limitations. In this paper, we utilized this theorem by Semiretti and Wu, and the key bottleneck is that the theorem does not tell us the AP explicitly. So if we know the arithmetic progression explicitly, or even we just know its common difference, then our algorithm and the analysis can be much simplified. And moreover, if we can know, so if not only we can know the AP explicitly, so it's further desired that we can know which element add up to each AP term. So indeed, currently our algorithm can only solve the decision problem. If the answer is yes, it cannot return a solution. And this issue actually also exists in the dense subset sum problem. So it really makes sense to revisit those important additive combinatorics results and restudy them from the perspective of algorithms. Okay, so finally, I will conclude with a bunch of open problems. And the most important one in subset sum relevant research is whether we can get order of n plus w. And another problem is how to find a solution as efficient as the decision problem. I think this is very much related with the last open problem. So can we obtain algorithms for relevant additive combinatorics results in preferably near linear time? Remember that the reason we are using additive combinatorics is that we can skip the computation when the computing cost is too much. But it seems that if we do so, we will lose track of the solution. So in other words, additive combinatorics works in these settings, but not in a perfect way. A constructive version of the additive combinatorics result, not just an existence claim, will be very useful. And this is the end of my talk. Thank you very much.